Okay, the notes that you see here are going to be for section 6.4, which is the last section that we'll be doing for the course. We're going to talk about work-related problems, which is really just one application of integration that would be important to scientists and engineers. And we're going to look at the work required to move an object. Okay, so like when you carry a refrigerator up a flight of stairs or push a stalled car, you apply a force that results in the displacement of the object and work is done. Okay, now in everyday language, when you talk about the word work, you're describing the effort required to perform a task. In physics, it has kind of more of a technical meaning that depends on the idea of a force. Let's look at, here's a definition. If an object moves along a straight line with position function s of t, then the force, capital F, on the object in the same direction is defined by Newton's law, a second law of motion, as the product of its mass and its acceleration. Okay, and you'll notice that I'm using Leibniz notation there. Of course, the second derivative of the position function is how you calculate the acceleration for the object. There are many types of forces. Centrifugal force, which is the tendency of an object to following a curved path to fly away from the center of the curvature. Just an example would be like if a ball is swung on the end of a string, it will exert a centrifugal force on the string, tending to break the string and fly off on a tangent. Okay. There's electromotive force, okay, and that would be a source of energy, like a battery that can cause current to flow in an electric circuit or a device of some kind. Gravitational force, the force due to gravity. So those would be a couple of examples of where we would see, forces in nature. A force can be thought of as a push or a pull. Therefore, a force changes the state of rest or the state of motion of a body. For gravitational forces on Earth, it is common to use units of measure corresponding to the weight of an object. So weight would be an example of a force. Okay, here's another definition. If the object is moved a distance of d units in the direction of an applied constant force, capital F, then its work, which we'll call capital W, is defined by the force times the distance. Okay, now keyword here is constant force. We're going to look at a variable force later on. Before we look at some examples, though, there's some measurement notes that we need to know. First one, in the SI metric system, the mass is measured in kilograms. The displacement is measured in meters. The time is measured in seconds, and the force is measured in newtons. 1 newton is defined to be 1 kilogram times 1 meter divided by 1 square second. Okay, now I've got an arrow here. In the SI metric system, the unit measure for force would be a newton. Okay, and you can see it's mass times acceleration, the acceleration due to gravity there. In the U.S. customary system, the fundamental unit is chosen to be the unit of force, which is the pound. Okay, and so one of the things that I'd like us to do, early on in the problem is identify which system we're in, if we're in the SI metric system or the U.S. customary system. Now we're going to know that right away because of the units that would be either provided in the description or provided in the picture that are given there. Okay. If the force F is measured in newtons and D is in meters, then the unit for work is called a Newton meter, which is also called a joule. Okay, and capital J will represent joule. If the force F is measured in pounds, then you're in the U.S. customary system, and the distance is in feet, then the unit for work is called a foot-pound. Okay, 1 foot-pound is about 1.356 joules, and 1 joule is about 0.738 foot-pounds. Okay, if you wanted to convert between one system or the other. Now, there's no problems where we're going to have to convert from one system to the other system, but these would be the conversion formulas that you would need if you were to ever want to do that. All right, let's take a look at some problems involving a constant force. So problem 1, how much work is done in lifting a 1.45 kilogram book off the floor to put it on a shelf that is 0.9 meters high? Use the fact that the acceleration due to gravity is 9.8 meters per square second on Earth. By the way, assume that in general you're doing a calculation on Earth. Okay, even though your mind might be in Pluto or somewhere else, G is always going to be 9.8 meters per square second on Earth. So let's find the work done. Work is defined to be force times distance, right? And force is defined to be mass times acceleration. So I'm taking the force times the distance. The distance that the book is going to be lifted is 0.9 meters. Okay, and then the force, mass times acceleration, the mass of the book is 1.45 kilograms. Okay, the mass is measured in kilograms there, they said. And the acceleration due to gravity is 9.8 meters per square second. Okay, so all I would have to do here is multiply these three numbers together. Now, if you have kilograms times meters divided by square seconds, that is by definition how we define a Newton. So when I multiply these first two numbers, I'm going to have 14.21 newtons times 0.9 meters. That would be 12.789 Newton meters, which is the same as 12.79 joules. Of course, make sure that the units are included when you give your answer. Just like any other story problem, that's we'd want that to be there. Okay, here's another example. Problem 2, find the work done in lifting a 50-pound box 4 feet. Well, again, we're going to just simply take force times distance. Now, this time I'm in the U.S. customary system, and the pound is represented as the unit for force. Okay, so we've got a 50-pound box, that would be F, and we're going to lift it 4 feet, D would be 4. So all I got to do here is multiply these two numbers, and I'll get 200 foot-pounds. Okay, there's a note here. Unlike problem 1, we did not have to multiply by G, right? I didn't do that here. Because we were given the weight, which is a force, okay, and not the mass of the object. The weight of the object already takes into account the acceleration due to gravity, and so there's no reason to multiply by that number if that's already been figured in. Another note that I want to mention here, I will see students on occasion do this. When you're in the U.S. customary system and you calculate work, it's foot-pounds, not feet per pound. Okay, feet per pound is totally different. Okay, so again, make sure that you're getting the correct unit measure when you provide that at the end when you give your answer. Problem 3, find the work done when a force of 112 newtons is required to slide a cement block 4 meters in a construction project. Okay, so in the SI system, the unit measure for force is a Newton, and the distance is in meters. And I'll just simply multiply these two numbers together then, and I get 448 joules. Okay, or 448 Newton meters is the same thing. Now, another thing to mention. So I realize that terminology that we see here is not really something that a lot of people use in everyday language. Okay, joules and foot-pounds and things like that. All right. But like any other story problem, you'd want to get an idea, at least have an idea if your answer is reasonable. Okay. Now, in comparing like problem 1 to problem 3, okay, lifting a book versus sliding a cement block in a construction project, I mean, those would be two different things there, right? And so the numbers that you'd expect ahead of time would be drastically different. Okay, and in fact they are, so get an idea for, how the numbers should look, based on previous examples and that. Now, in the previous examples, the force involved is constant. Okay, so there's not really a difficult thing here, in my opinion, for these first 3 problems. All you're doing is multiplying 2 numbers or 3 numbers, right? And like anybody can do that. Okay, but that's when the force was constant. Now, in the problems that you guys will have, there's going to be a variable force on most of them. Okay, if a variable force is applied to an object, then calculus is needed to determine the work done. Okay, and the reality also is that, in just an ordinary example, there is typically going to be a variable force going on. Okay, if I go back to like these previous problems here, like it's highly unlikely for the force to remain constant unless it's being done by a machine or something like that. But if you're lifting a box, like the force is going to vary, likely. Okay, or if you're sliding a cement block, like the force, the work that is going to vary in that. So calculus is required to determine the work done when we have a variable force. Here's a definition. If an object is moved along a straight line by a continuously varying force f of x, then the work, W, done by the force as an object is moved from x equal a to x equal b is defined as an integral. We have the definite integral going from a to b of f of x dx. Okay, so problem 4. Suppose that we want to calculate the work done when a force of the square root of x plus 2x pounds is required to move an object 9 feet along the x-axis. Now, of course, the first observation would be to notice that this is a variable force, right? X is the variable, and x is going to vary. So in this problem, it's not going to be just to multiply 2 numbers and you're done, okay, like I was doing before. But instead, when I calculate W, I want to use this integral formula. We want to move the object 9 feet along the x-axis, so the bounds are going to be going from 0 to 9, and I'll want to integrate the square root of x plus 2x on that interval there. And, of course, make sure your notation looks good. The integral sign, the dx. The antiderivative is 2/3 x to the 3 halves plus x squared. The 2's would cancel there. And then we're evaluating this from 0 to 9. Okay, plug in your bounds. 9 to the 3 halves, well, 9 to the 1 half is 3. 3 cubed is 27. Divided by 3 is 9, and then times 2 is 18. And then 9 squared is 81. Minus, when you plug in 0, both these terms are going to be 0. And when you add these together, 99 foot-pounds would be my answer. And of course, another thing to notice early on in this problem, but really before you calculate anything, is that you're in the U.S. customary system, right? The fact that they've told me pounds here and not anything about newtons or meters or anything like that, we're moving the object 9 feet, that's in the U.S. customary system, means that I could know, like I said, before I calculated anything, okay, my answer is going to be some number in foot-pounds would be the units that I'd provide at the end there. Okay, we'll look at some more applications of a variable force coming up in the next video here.